In this video, we want to look at the nuclear charge and shielding or screening. Alright, the concept of nuclear charge is all about the electrostatic force of attraction or pull of the positive nucleus on the surrounding electrons. Now, we know before now that the nucleus is positively charged due to the presence of protons in it, and then the surrounding electrons are negatively charged. Of course, we know that unlike charges attract. So if you have negative and positive, there will be this attraction. So generally, the nucleus pull inwardly on the electrons surrounding it. Is that okay? Now, those orbitals that are closest to the nucleus feel the fullest nuclear charge of the nucleus. They feel the complete force of attraction of the nucleus, which therefore means that any electron on these orbitals closest to the nucleus will experience the greatest nuclear charge. Now, this force of attraction or pull that the nucleus exerts on the orbital closest to it, and hence on the electrons on that orbital, this fullest force of attraction is known as the actual nuclear charge. The actual nuclear charge. Because like I said, the orbital closest to the nucleus will feel the greatest attraction. Does that make sense? So that value that we get as a result of that attraction is the actual nuclear charge on the orbitals closest to the nucleus. Please permit me, let's just quickly sketch something here, just a little. Imagine I have this as the nucleus. You have the first shell having its orbital, you have the second shell having its orbital there. Now you notice that there are distances measured from the nucleus to the shells, and as you continue to add new shells, the atomic radius increases and hence the atomic size. No wonder we know that one of the trends in the periodic table regarding atomic radius or atomic size is that it increases down the Watt group. This is because the distance away from the nucleus increases, gets bigger as you add in new shells. Alright, now this shell with red circle here that is closest to the nucleus will feel the greatest nuclear charge of the nucleus. Let me put plus here. The nucleus will pull on the electrons on this red orbital more than they will pull on the electrons on this blue orbital. I hope I'm communicating. So this orbital that is closest to the nucleus, the force with which the nucleus is pulling on it, on the electrons found on that orbital, is what we call the actual nuclear charge. Because in that case, there is nothing that is separating the nucleus from the electrons on that orbital closest to the nucleus. So the nucleus has direct influence, on this closest orbital. But as we mentioned, as you add new shells, the atomic size increases, the atomic radius increases, the distance away from the nucleus increases. And what do we expect on this force of attraction that the nucleus have and the electrons? Of course, it's going to reduce. That reminds us of Coulomb's law, alright? Coulomb's law. Coulomb's law of electricity, that the force of attraction or repulsion is inversely proportional to the square of the distance, between the charges. And so we have that formula in physics as F equal to K Q1 Q2 all over R squared. That R squared is the distance, So the nuclear charge, in this case now, will reduce due to the greater distance that is found. In fact, the relationship is that it decreases, that is the actual nuclear charge decreases inversely to the square of the distance of the electrons away from the nucleus. So we'll have something like this. Always remember Coulomb's law, it's going to make you understand this explanation here. Alright, now when you add a new shell to an atom, what happens? You don't just add the shell, you add in order to be able to add new electrons. Is that not so? Now, just look at this. We have electron in this inner shell, and we have electron in this outer shell. Now, when you added this new shell, it warranted that you needed to add another electron to the new shell. What is going to happen? Apart from the fact that the distance from the nucleus to the outer shell is now greater, you will agree with me that this inner electron will repel the outer electron. The inner electron will be pushing the outer electron away, because these are the same charges, so there will be repulsion. That repulsion is known as shielding or screening. So these inner electrons in an atom, they usually shield, they usually screen, they usually push away the outer electrons from the attractive influence of the nucleus. Because in this case now the nucleus no longer have direct link to the outer electrons like that. So the effect of the actual nuclear charge will be reduced. And what is responsible for these? The inner electrons, which we call the intervening electrons. We call them the intervening electrons, you know. These intervening electrons, they push these outer electrons away due to repulsion. So if you have the nucleus here, as this electron is pushing this one away, this nucleus at this point will find it difficult to exact the actual force of attraction it is exacting on this one. It will find it difficult to exact the same force of attraction on the one that is farther away. So the point I'm trying to highlight here is that the inner electrons, they also help, you know, to reduce the actual nuclear charge by doing what? Repelling the outer electrons away so that the nucleus will have less pull on the outer electrons. All of these things being explained, what is the main point there? It leads to a reduction in the actual nuclear charge. That reduction in the actual nuclear charge is known as the effective nuclear charge. The reduction in the actual nuclear charge as a result of the intervening electron is known as what? The effective nuclear charge. We're going to use Z effective to represent that. In the next video, we're going to see the formula of Z effective as to how it is related to the actual nuclear charge and a constant as a result of this screening, which we're going to call the screening or shielding constant. In a previous video, we explained the concept of the effective nuclear charge, and we stated that the effective nuclear charge Z effective is the reduction in the actual nuclear charge as a result of what? The inner electrons, the intervening electrons. Now, what is the relationship between the effective nuclear charge, the actual nuclear charge, and a constant known as the screening constant? Of course, equation alpha here gives us the relationship. The effective nuclear charge is equal to the actual nuclear charge minus the screening constant. In this equation alpha, we do not have problem getting the value of Z, actual nuclear charge, because it happens to be the atomic number of the atom we are dealing with. So if we're talking about maybe calculating the effective nuclear charge by the s orbital of maybe the atom chlorine, then we know that the actual nuclear charge for chlorine will be 17 because chlorine is atomic number 17. Our problem in using this equation alpha is the determination of what? This screening constant, because the truth is the screening constant value differs for different subshells, SPDF. And not only that, it differs for different subshells. Even when you consider a particular subshell, depending on the orbital of that subshell you are dealing with, the value still differs. So it's very important for us to know how to calculate this screening constant. And good enough, an illustrative picture to how we obtain this screening constant is given by a rule known as the Slater'S rule. Slater'S rule. So we're going to look at that in the next video. Is that okay? It's a simple one anyway on how to calculate this screening constant. It's important that you are aware of this order, the value of or the magnitude of the screening constant with respect to the subshells. The screening constant by electrons in the S subshell is higher than those in the P subshell, which means that the electrons of S subshell, they screen higher more than the electrons in P subshell. P screens higher than D, and electrons in D, they screens higher, they shield higher than the electrons in F. So take note of that order. When we come to the periodic table, what is the behavior of this screening constant and effective nuclear charge in the periodic table? Alright, so we'll talk about trend, just like we know of electronegativity, electropositivity, atomic radius, ionization energy, and the rest of them. Okay, so this screening constant, when you're coming down the group in the periodic table from top to bottom, so it becomes a particular group from top to bottom. Alright, the value of these screening constants increases down the group. But when you're going across the period, you know, from left to right, the screening constant value will decrease. Take note, that's point number one here. Then point number two, the effective nuclear charge, this is inversely proportional to the screening. And that is true, you know. See, this actual nuclear charge is constant for a given atom. But this screening, the value differs for that particular atom, depending on the subshell you are considering. Are you getting me right? So this value differs. If this value increases, that is the screening constant value, if it increases, you would notice that Z effective will decrease. Just imagine you're talking about chlorine now, and then for that same chlorine, atomic number 17, so Z is 17. Let us assume you calculated maybe the screening constant for, let's say, 2s orbital of the subshell S, and you get, say, 4. You get 4. You know that the effective nuclear charge in that case will be 17 minus 4, giving you what? 13 as effective nuclear charge. Remember, we assume that the screening should be 4 in that case. Alright, now what if you now calculate for another orbital of the subshell X, and then the screening constant for that chlorine in that orbital you choose to calculate for now, the screening constant is, say, 10. If the screening constant is 10 in that case, you see that the screening constant has increased from 4 to 10. Z, which is 17, will be 17 minus 10. So that the Z effective, the effective nuclear charge will now be what? 7. So do you see the difference? When this screening constant was 4 for chlorine, the effective nuclear charge was 13. When the screening constant increased to 10, the effective nuclear charge decreased from 13 to what? To 7. So of course these two quantities, they are inversely proportional. Therefore, the behavior of the effective nuclear charge in the periodic table will be completely opposite to that of the screening constant. Is that so? So what do you expect? Alright, so you look through this, okay? The effective nuclear charge will decrease when you're coming down the group from top to bottom. But when you're moving across the period from left to right in the periodic table, the effective nuclear charge will increase. In the next video, we shall look at Slater'S rule, and then we'll apply that rule in solving to obtain the effective nuclear charge value for a given atom, of course, from the screening constant value. Yeah, now we want to look at the Slater'S rule. John C. Slater presented an illustrative rule that can help us to determine the value of the screening or shielding constant. Of course, you recall that I stated in the previous video that once you know the value of the screening constant, then our problem is as good as solved in determining the effective nuclear charge. So how do we get the value of the screening constant? On the board here, we've considered the screening constant value according to Slater'S rule for the S subshell, the P subshell, the D subshell, as well as at the periphery of an atom. So let us quickly look at them. Please take note that it's required that you memorize these rules, and so that when problem is given to you, based on the subshell that the question is asked on, you would know the one to use. The first one is Slater'S rule for electrons in NS or NP subshell. Simply, any electron in the S subshell or P subshell, you are asked to calculate the screening constant value, of course, for which you can obtain the effective nuclear charge. What would you do? So this is the formula. The screening constant value is equal to 0.35 times number of electrons in the N shell minus 1. The N shell is that particular shell that the question is based on. Could be that you're asked to find the effective nuclear charge for the electron in the 3s2 subshell. Is that okay? So that end shell is that 3s2 subshell. Take note, the end shell is that particular shell that the question is based on. So it's going to be 0.35 times the number of electrons in that shell minus 1 electron. Which means if you're calculating based on 3s2, 2 is the number of electrons there in that end shell that your calculation is based on. Alright, so it will be 0.35 times 2 minus 1, because the number of electrons in that end shell is 2. You have to subtract 1 from it, which eventually becomes 0.35 times 1. Is that not so? Alright. It simply means that the electron in that end shell contributes 0.35 to the screening. You're going to add it to 0.85 times number of electrons in the n-1 inner shell. Are you following? N-1 shell simply means all the shells before this end shell. So once again, if your calculation is based on 3s2, you now need to ask yourself, what are the shells n-1? N in that case is 3, so n-1 will give you 2. So all the subshells bearing 2, 2, 2. Okay, the number of electrons there is what you're going to use in multiplying 0.85 here. Then plus 1.0 times number of electrons in the rest inner shells. Of course, after that too, the next inner shell is simply the 1s. Is that not so? So that's what we mean by the rest inner shell. Okay, think about a situation where your calculation is based on, let's say, the 4s2. Okay, in that 4s2, you take note that you have things like 3p. Is that not so? You have 3p, you have things like 3p and then 2p, 2s, and the rest of them, even 3s. So if calculation is based on 4s, your n shell will be that 4. Are you following? Then your n minus 1 shell will be all 3 shells, principal quantum number 3. Why the rest inner shell will be from principal quantum number 2 down to principal quantum number 1. Anyway, we're going to see how this calculation is being done in the next video when we solve question on it. Please take note, if the calculation is specifically based on 1s subshell, you no longer use 0.35 in your multiplication. You're going to use 0.3. Look at it, okay? 0.3 to multiply the number of electrons in the n shell minus 1. Does that make sense? So these values are the contributions by the electrons in the given shell. Now let us move on to a situation whereby the electron is now residing in the d orbital. If the electron is residing in the d orbital, the formula you use to calculate the screening is 0.35 times number of electrons in that nth d orbital. Are you feeling right? Or shell, then minus 1. That's in that particular d orbital that the question is based on. Subtract 1 electron from it. Whatever you get there, use it to multiply 0.35. So just imagine that your calculation is based on 4d orbital. And maybe you have 4d9, for example. Then the n shell there is the 4. Okay, so the number of electrons there will be 9 minus 1, which you're going to put in here. Okay, it's going to be plus 1.0 times number of electrons in the rest inner shells. Did you take note that there is no 0.85 in that formula there? So once you multiply 0.35 by the number of electrons in the n shell, where your question is based, minus 1 electron from it, all you need to do now is 1.0 times the number of electrons in the rest inner shell. Take note, not outer shell. In fact, any electron in a principal quantum number greater, higher than the principal quantum number that your question is based on, those electrons in higher principal quantum number do not contribute anything to the screening. Take note of that. Of course, we already stated in previous video that screening is due to the intervening electrons, that is electrons in the inner shell. Okay, the third part here is when you now consider all the electrons in the atom. That is the situation you're asked to calculate the effective nuclear charge at the periphery of an atom or an ion. So what do you do about that? The screening is equal to 0.35 times number of electrons in the n shell. Did you take note that in this case there is nothing like minus 1 electron anymore? So if the atom, the last shell, let's say is 3s. If the last shell is 3s, maybe 3s2, then of course you're going to do number of electrons in that last shell using to multiply 0.35. Is that okay? Then plus 0.85 times number of electrons in the n minus 1 shell. I've explained that concept here. Plus 1.0 times number of electrons in the rest inner shell. Alright, you can get through the note here. I explained that already. Electrons in higher principal quantum number above the one that your question is based on do not contribute anything to the screening. Hence, you don't use those electrons in your calculation. I think it is time now we want to apply Slater'S rule to obtain screening as well as the effective nuclear charge offered by an electron in an atom.